And Cassie. Poor Cassie. Hi, guys. We miss you. All right. We have been talking about pep rallies and every other sort of randomness. Alec wants to go to Woodstock. Anyway, so section 2.6, they started taking notes. We are going to go grade section 2.5, but I wanted to show them where we're headed. We're going to take 2 days on this section, so today and Monday, even though it's not, I don't think, super long, but it does have some stuff. So we're going to take 2 days on this. The homework's going to be due on Tuesday. Just a quick heads up for you guys. I probably will be gone Monday. But I will not be gone. I mean, I will. My body will be gone, but my soul will still be here, kind of. Because you'll be listening to last year's class, finish section 2.6. Sound good? So you'll be watching a video of last year's class, finishing 2.6. So it's going to feel like a normal class. You're going to be taking notes. Well, it's going to feel probably like an abnormal class, because it's going to be a class where we get things done, or we got things done every day. We do eventually. But you might not be able to have your normal, like, just chill and talk sesh with this sub. Yeah? Sound good? So Mrs. Ashdale, be nice and kind and sweet to her because she's a really good sub. She knows her math, and she cares about math lessons. But you are going to be listening to me, sadly not able to talk to me. Or I guess you can, but it'd be a little weird. Teach last year's class the end of this section. Good? Cool. And then I'll be back on Tuesday, and we will grade section 2.6. We'll start reviewing for our test. That will be bumped a day on the calendar. Oh, sorry. No, we do have section 2.7. Oh, Santo.
Wait, we didn't do
Tuesday, we'll do 2.7, and then Wednesday we'll review for the test.
We don't have a quiz this week.
Nope, just a test. 2.1 to 2.7, and then we're going.
I have a lot of work.
So a few of you guys this weekend might want to, if you've missed any class or if you've fallen behind in any notes or homework, try to catch up. Because that'll make next week easier. Sound good? I'll be here today.
Yeah.
Just not Monday. I'll be back.
No, I mean like after.
Yeah.
I'm okay.
All right. If you guys don't mind, I'm going to go ahead and Alec, focus, please. Thank you. I know it was a little boring, logistical.
Please.
Reply.
Please.
Are we not going over
We are, but I want to cover these 2 pages first, okay?
Oh, okay.
So here we go. Rational functions, ratios. Ratios, fractions. Fractions have numerators and denominators, right? Oh, my computer. Come on, let's go. Wakey, wakey. It needed broccoli bread.
I want broccoli.
Okay.
Projector shifted.
Yeah. If you guys notice, it's just a little bad. And whichever way I do it, it can't possibly fit nicely without being really tiny and small, and it wouldn't fit.
Mr. Hart.
We wouldn't be able to read it.
I used to click the button, it was like move like one
It was
stick
so
for a
funny.
second.
I like.
Good job. Mr. Hart, team, it's math time. So, here we go. Rational functions. We have numerators and we have denominators, yeah? So we have tops and we have bottoms. On the tops, or on the numerators, we can use them to find some cool stuff. On the bottoms, we have to be really careful because anytime we have denominators, what do we need to remember? And that's what goes in the blank, I do believe. Don't we have domain problems? Right? G of x can't be 0. So, if we find zeros at the top, it's going to tell us something, and zeros at the bottom are going to tell us something. Zeros at the top are going to tell us the zeros of the function, and zeros at the bottom are going to tell us the DNEs. Speaking of DNEs, they have a snazzy name, and the snazzy name is discontinuities. DNEs have a name, discontinuities. Because continuous functions, you can draw them smoothly with your pencil without picking it up and having to go back down. There are no breaks, no jumps, no holes. Peanut gallery, shush. Discontinuities are places or points where, or characteristics where, my graph is broken. Maybe just broken at a point called a hole. Or maybe broken at a whole line called a vertical asymptote. Hey. Or maybe broken in another way with a piecewise function. But to get ready for those discontinuities, super important word, super important idea. Not just for now, but for later. Let's just talk about what we already know, which is domain. What we already know is domain, right? Yeah. So, domain. We look in denominators and say, hey, you can't be 0. So whatever is down there, we just take it out. Take the g of x, the function, whatever is there, take it out and say you can't be 0. So we actually saw rational functions in chapter 1 anytime we saw a denominator that we were trying to find a domain for. That was a rational function. We were dividing by a function. There was a ratio.
So if x plus 2 is on the top, you wouldn't be trying to.
It wouldn't be rational, yeah.
What
would just be a polynomial.
Okay, so you wouldn't do anything.
And so we solve, and x can't be negative 2. Quick reminder, just because, why not? It's math, we're supposed to remember stuff. Remember that we could write this in interval notation, but we don't have to. I don't mind the shortcut way of just x can't be negative 2, but we could use intervals too. It's okay. But let's talk about discontinuities. Okay, discontinuities, places, times, x values, where the function is somehow broken, somehow does not exist. There are two different types in rational functions: poles and vertical asymptotes, removable and non-removable discontinuities. Poles and vertical asymptotes, removable and non-removable discontinuities. Now the nice thing is, guys, I've totally tried to give you a hint as to what's going on because I say can be, right?
Right.
Oh dear. That's horrible grammar.
When x minus a b factored.
B factored out. Yay! B factored out. That's great. How about can be factored out? Does that sound better?
That's better.
Yeah, I know. Okay. We factored out. What can be factored out? Oh dear.
I wrote can potentially do.
Go for it. Do whatever feels right. That's not always the best life motto, but sometimes. Can be factored out. Removable. These go together. Can be factored away, removable, and can't be factored away goes with non-removable. So check it. In this top example, you guys already have it written. Sorry, it's light. But can't I rewrite this to be t plus 1 times t minus 1? Isn't that a difference of squares in the top? What happens to the t plus 1 since they match? After factoring, if they match, I can reduce. And when I reduce, I'm factoring it away. I'm factoring the denominator away. I'm factoring the problem away. If problems happen in the denominator, and if I can factor it away, if I can factor and reduce, well, then it can be removed. But do you guys remember when we did, what was your question? The long division. When we did the long division, and then in the book answer key, it had the whole like r can't equal, t can't equal, x can't equal after the division-y part. That was because you could factor away that denominator, but the domain problem still is there. T can't be negative 1. So there is that whole little, okay, there was a problem, but if he can be factored away, if he can be removed mathematically, which he's still there on the graph, but this is just the hint. If he can be factored away, that problem is just a hole. So if we were to go to negative 1, well, actually, here's the cool thing. If we were to go to negative 1, and if we were to plug in negative 1 to what's left after we ignore the denominator or remove the denominator, negative 1 minus 1 is negative 2. I even know where the hole is by plugging in, not here, because plugging in here, if I plugged in, oh, that should be a t. Oh dear, I had major issues on this page. F of t equals t squared minus 1 over t plus 1. I would get 0 over 0, which does not exist. I can't plug it in here because it won't exist, but I can plug it in there and get negative 1, negative 2. That's my hole. And how do I know that this is my graph? This is a nasty function. That's disgusting. How did I know it was just a line?
Because it's just t minus 1.
This is the exact same as that, just with a hole.
So I don't understand why t can't equal, where you got the t can't equal negative 1 from.
Because of the beginning.
Oh, so when we...
So at the very beginning, I can say domain, right? At the very beginning, thinking of the original domain problems, t can't be negative 1. But the really cool thing is if it's a hole, I get to actually know who this guy is except for the hole.
How do you know
He's
it's a hole?
Oh, because the discontinuity can be removed. Let me show you a vertical asymptote and you can compare and contrast. Laura. Oh, I thought of what would be... f of negative 1. Can't really write that. Maybe it's not good for me to write it like this. Maybe I just point to it. Is that okay? I got the negative 2 by saying, okay, I know he's illegal. I'm supposed to put a hole there. But where would he be if it didn't work? And so I plugged it in. Negative 1. this beginning gross division of a quadratic over a linear, but when I divide it, it's just a line. What line? Oh, a line with a hole. Because of that original domain mistake. But he is this line. He's this line in its entirety. Just when I get to this one point, I have to put my phone. Sophia.
Is text corrections due today?
No, Tuesday. Non-removable discontinuities. Okay, so what's different? Because Jaden was like, how do you know this one? Okay, hold on. Up here, holes can be removed by factoring away. So, vertical asymptotes. Well, okay, hold on. We still do domain the exact same way we did domain before and say, he has a denominator. Since he has a denominator, I know that 2 plus x can't be 0. X can't be, are you guys okay with me just jumping? Can't be negative 2. Right? Okay. So, just like old school, just looking at this function, I know x can't be negative 2.
And it can't be 0 either, right?
Well, 0's okay. Because if I plug in 0, 7 plus 0 over 2 plus 0 would be 7 halves.
Oh, okay.
See it? But the bottom, the whole bottom, can't equal 0. So technically this comes from me saying, hey, you can't be 0. And then when you solve, you get x can't equal negative 2. Okay. That just looks messy. I'm just going to erase. Okay. But up here we said, oh, factor and simplify. Well, this one, though, if you try to factor, I guess we could rewrite it like this if you really want to, but even though this looks nicer, like, guys, can I factor away anything in the top or the bottom?
No.
I can't
No, it's
take out a
binary.
2. I mean, not nicely. I can't take out a 2, not nicely. Now, some of you, my poor little subconscious kitten killers, you gotta squelch the urge. Some of you were like, yay, let's get rid of the 2's and let's get rid of the x's, and why not? Let's get rid of the pluses, and all I have is 7.
Yeah.
I like that.
I'm glad you like it. It's so horribly wrong, and kittens died too, to be
Nobody
exact.
cares
Is
about
that
kids.
bad for you though?
Okay, stop.
No, you know what?
Mathematically, yes.
Snapping through those premise.
Focus. Focus. If I group numerator and denominator, my question is, do they match?
No.
And if they don't match, I cannot reduce. So non-removable, I cannot remove, factor away. Does that make sense? Now, if I was to plug in, if you guys wanted to try, I could try to plug in, just like I plugged in negative 1, 0 over 0. It does not exist. It doesn't work. I could plug in negative 2. And if I plugged in negative 2, 7 minus 4 is 3 over 0. This one also does not exist, but can I give you guys a hint real fast? If you don't like this whole removable, non-removable, factor away, and can't factor away, if that doesn't stick for calculus, it's super helpful to realize when you plug in a discontinuity and get a number over 0, DME, you will always have a vertical asymptote. And for calculus, it's really helpful to know if you plug in a discontinuity and get a 0 over 0, DME, it's always a hole. It's a silly shortcut, but it's a cool shortcut. They both do not exist. They're both discontinuities, zeros of the denominators, but how they do not exist, whether you get a number over or 0 over, if it's really hard to factor and you're not exactly sure, you can always double check and say, wait, does it even factor? If you have 0 over 0, yes, it will. It is removable. It is a whole. It's possible. But if you get a number over 0, not possible.
Wait, why'd you do that for negative?
Because he was my problem.
So you just did that just to plug it in?
This is like a little baby other test that will always point us in a certain direction.
Okay.
Plugging in the discontinuities.
So is there a way to, you're not graphing this at all then? is it?
I'm
Like,
not,
you
but
can't.
technically what I could do, just by knowing this, is I do know at negative 2, unlike this one where I went looking for, Laurel was asking how I looked for, I went looking for the point by plugging into what was left,
Yeah.
and made a hole. This one, nothing went away, so I'm like, I don't know what's going on, but I do know.
That's the vertical asymptote.
There's a vertical asymptote.
Okay.
And I do know, well, do you guys know? When you come into a vertical asymptote, what always happens?
They'll in-
Right? Now, hold on. Are there different ways to split?
Yeah.
You can split this way or that way, or they can agree up or agree down. So there's different ways of splitting. Guess what? Later in the section, we're going to actually figure out how to know how it splits. Whether they go opposite one direction or the other, whether they go together, up or down. There is a way to test and there is a way to know, but we have to learn that later on. Sound good? But for right now, we know there's a vertical asymptote. section. Hold on, pause. Let me recalibrate with how much time we have left, which is 5, 10, 15. Okay. I'm going to go one more page. Because this one more page is exactly what we just talked about. How do we know what's going on as you have a vertical asymptote? Because as you noticed, with the hole, man, that guy was easy to graph. Because I get rid of that discontinuity. I have a polynomial, which I kind of know how to graph. It was the line. I put the hole, and I have it. The vertical asymptote, I drew a dotted line and said, well, that was fun. I don't know. Unless I know what happens as the function comes in towards the vertical asymptote. But here's the dealio. Didn't we just say you have to come in towards the vertical asymptote from both sides, right? So I have to check both behaviors because maybe they agree, maybe they disagree. I have to come in from both sides of the excluded x value, which is the same thing as the discontinuity, aka the
DNE.
yeah, the DNE or the DA, the DA. However you want to think about it. It's the DNE point or it's the vertical asymptote point. It's the discontinuity. Bless you. Oh my goodness. At x equals c. Here's the cool thing. Every time we have a dollar sign, every time we have a vertical asymptote, every time, remember, checking at the discontinuity, every time we plug in, and don't just see an over 0, but a number over 0. We know that the function, as it comes in towards that, is either going up or down. We know the function is either going to positive infinity skimming, or negative infinity skimming, or negative infinity skimming, and positive infinity skimming, or positive positive, or negative negative. Somehow, we know that function is, because of the skimming nature of a vertical asymptote, f of x is either approaching up forever or down forever. So the nice thing is, before we even go testing and trying to figure out, it's one of two answers. 50% chance of getting it right. So how do we know? Now, if you have a graph, you can see the function. Sorry, is it too small? No. It's negative 3 over x plus 1. Is that a little bit better? It's negative 3 over x plus 1. If we had a graph, it'd be easy to tell. Because it's like, oh, hey, look, there it is. But we don't have a graph yet. And if we had a graph, well, we just answer it. So we'll get to the graph in a second. We'll figure out what this guy looks like and then talk about it. But let's, before we go to the graph and just find the answer, let's go to a table. Before we go to, actually, do you guys mind if I don't go to the table first? Can I go to the math part that doesn't need a calculator? Yeah. Is that cool? Not that I know some of you love your calculators and you, okay, but the point is we can't always use it. There is a math way where we don't even have to go to our calculator at all. So if you want, to be honest, this is my preferred method anyway, the math way. But you could leave a couple lines, just a couple. We'll be back to the table and the graph in a second. Well, let me show you how you don't even need your calculator. But you have to kind of, well, go carefully.
You have to use your big brain.
Kind of, but actually it's not even that big. Not your brain, but the need for it in this problem. Remember how we had as x goes to the right and to the left to positive and negative infinity? Remember that? For n behavior, as x goes to positive and negative infinity. Are we trying to go far away to the right or far away to the left? No, we're trying to get closer and closer and closer to one dude, to C. There's a snazzy way of showing that, just because you're in honors, there's a snazzy way of showing coming in towards the, oh, hold on. Who's my discontinuity of this one? X can't equal, do you guys agree with Sophia? Yeah, negative 1's the bad guy. And if we tried to plug him in, do you see how f of negative 1, it's not a whole, I get negative 3 over 0. Yeah. Another way of looking at it, I can't cancel, I can't reduce, sorry, him away. Anyway, he's a vertical asymptote, for sure. Not a whole, sadly. There's snazzy notation for coming in towards the vertical asymptote from the left or from the right, okay? from the left. Not to the left, but from the left of the vertical asymptote. And from the right. And don't worry, in chapter 12 this comes back and we'll like study it, memorize it, make sure we have it down. Why is there a little negative? Why is there a little plus? I don't know. Sorry, it's just notation.
It's a cat icon.
Sadly no, but it's clever that we thought of it. So
I think it's horizontal for sure.
it's actually x coming to c, but just a little bit below because it's from the left. So numbers that are a little bit on the left of it on the number line, and numbers that are just a little bit above it on a number line. So for our example, if we're coming from the left of our vertical asymptote, we are going to pretend, we are going to picture, we are going to check the sign of what would be happening at f of, what's something just a little bit to the left of -1? Oh, but that's so far away, that's like a whole unit.
Oh, bruh.
-1.1, that's better. If you even do -1.01, it'd be super snazzy. Or -1.001, but how about -1.1?
-1.02.
Ooh, alright, sure, go for it. Now, if I was trying to do this, right, wouldn't I need to plug this in the x box? So -3 all over -1.1 plus 1. Now here's the really cool part. You ready? We're trying to answer the question, what is the function doing as x is coming in towards, oh dear, the vertical asymptote from the left? This vertical asymptote is technically that -1. We're trying to figure out its behavior. We're trying to answer with f of x is approaching somewhere. What do we already know is a part of the answer? Looking at the two answer choices.
X is not
Infinity or negative?
Okay, so if it's infinity or negative infinity, don't we already know there is an infinity? We're just trying to figure out which one. What's the sign in front? Is it a positive or is it a negative? Well, I don't know. What am I telling you to do?
Check the sign.
All we need to know is the sign? Yes. We don't need to know the number value? Nope. Just the sign? Just the sign. So can you guys look at this and tell me just the sign of the final answer?
It's negative.
Why is it positive?
Well, yeah, we can't see
Because
the
it's a
sign.
negative.
It's a negative over, what is this going to be?
Negative.
A negative, because he's stronger, right? I don't care about the number at all. I already know it's going to be infinity because of what's going on, what type of discontinuity. I just need to know the sign. So if you guys can see, it's going to be a negative because the negative wins over a, sorry, a negative over a negative because the negative wins. A negative over a negative is a positive. Booyah. So I know if I was to make a graph of this function, as I have, Jaden, remember I already did that dotted line at -2.
Yep.
I know as I come from the left, my function is somehow going up.
Because it's positive.
From the left, positive means it has to go up.
Okay.
So let's come from the right. Maybe it's the same, maybe it's different. I don't know. So guys, how would you follow the same procedure to come from the other direction?
Let's check the opposite.
Check the sign. How about f of 0.9? I like it. If we did f of 0.9, -3 all over 0.9 plus 1. Oh, it's a negative though, right? Because we have to be really close to -1. So -0.9. Okay, it makes a little more sense. But don't I only have to check the sign? Who's this guy going to be? A negative over, isn't the positive now the stronger one? You see it? So 1 minus 0.09 is a positive. A negative over a positive is a negative. So I can answer my question and say, oh, f of x is going to the other infinity. So therefore, let's come over here and say, oh, I know what you're doing. You're going down. Now, does this tell me the entire graph?
New.
If we had reviewed yet, which we're not, we're going to later in this section, if we had reviewed the horizontal asymptotes, and if we knew the horizontal asymptote is at 0, put together with the vertical asymptote being at 0, maybe we would kind of have a better idea of what's going on. But we technically haven't reviewed horizontal asymptotes yet, so it's still a little bit dicey, but we at least know what's going on technically right around my vertical asymptote. Yeah. Going up and going down.
Misty.
Mhm.
So for the signs, so negative. Why on the top one? Why'd you use the two negatives to make a positive on the bottom when you use the negative and positive?
Oh, I just used something a little bit left of my vertical asymptote and something a little bit right of my vertical asymptote. Anything you choose a little bit left will get you a negative over a negative, and anything you use to the right for this problem will get you a negative over a positive. If I make this
Like on
subtraction.
the top, there's a positive there.
Oh, I see it here. I just chose with any addition or subtraction of negative numbers. Doesn't the stronger one win?
Yeah.
So 1 minus. I just showed like, hey, he's gonna win, so it's a positive number.
So since that
And
one's
he's gonna
bigger,
win.
since that one's big, okay.
I was just thinking ahead without having to write down numbers, and I was like, I know what's gonna happen.
Okay.
I know what's gonna happen. Sophia.
The
P.S.
VA,
Homework out. We're gonna grade.
the VA is the negative one or the
The VA is negative one.
oh, on the
Oh, sorry. Thank you, thank you. It's where the denominator is here. I'm so so used to having the most basic one at 0 instead. Thanks, Sophia. Yeah, we were at negative one. I don't know why I did multiple tick marks. We'll call that negative a half. How about that? And that's negative one. Let me show you the table real fast. You guys are just in your homework getting ready to grade. I just want to show you what a table would do, because to be honest, the math is the best way. If we had a graph, we could look at it and say, he's going up, he's going down. We could have answered the infinities properly. From a table, we could have come in closer and closer and seen it going down, 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 down. Negative infinity from that direction. From negative a half and negative 0.9, negative 0.999. If we had come in from the other direction, we could have plugged in negative 1.1 and 1.01, 1.001. We would have seen it. We actually would have seen it going up. But we don't have to do all that work. We don't have to put it into our calculator y equals and go to the table and plug in chug. We can actually just do a little bit of math. Where we say, we know vertical asymptotes, it's either going up or down, positive infinity or negative infinity. I just need to check the
Sign.
Thanks, Jaden. That's fine. Okay, let's go grade. Here we go. Section 2.5.
That was kind of hard, not gonna lie.
Yeah, it was. I know.
yeah.
Number 8 was one of those tests, was one of those lower upper bound things that I said you don't need to memorize, so you might have gotten stuck on that a little bit. You didn't need to memorize Descartes' rule of signs or the lower and upper bound rules, but I just gave you a vocab to see if you could find it in the section. And there was a snazzy theorem. But we have some tricks. Do our tricks for number 26, do they include finding all the plus or minus factors of 9 over plus or minus factors of 3? Yes. So you should have figured out all of these are your possible rational zeros. How did they get to 3? I don't know. Maybe they plugged in positive and negative 1 and neither of them worked, so they moved to 3. Isn't that what you would have done? I would have done that. Start with 1, but it didn't work. Oh. Start with negative 1, but it didn't work. Oh. But if you plugged in 3, it did work. Or if you did synthetic division with 3. Now, they do synthetic division this way. I do a little baby box. Whatever. If you do synthetic division, 3 goes in. And as soon as 3 goes in, KJ, here you go. Ready? It broke down, right? As soon as 3 went in, the synthetic division broke it down to a quadratic. And now we have a quadratic. Awesome. Let's go. And then they went ahead and factored it using probably the x method, and then they said, hey, x equals 3, and x equals 1/3. So, multiplicity of 2, but still one number and 1/3.
Misty.
Yeah.
I was confused on finding the rational, like the possible.
Oh, because this doesn't show it to you the way I show it to you. Yeah. I would have taken member factors of 9, the constant term.
Oh, so you got I did not.
Does that make sense?
Yeah, I didn't think of it. Okay, so.
And then you just do 1 over 1, 1 over 3, 3 over 1, 3 over 3.
Wait, why do you cross?
Well, because it's all possible combinations.
Okay.
See it? All possible combinations. And so technically, if you're thinking of plugging in, I don't want to go plugging in 1/3.
Yeah. So
they usually think of the 1s over 1 first, like the 1s and the 3s and the 9s. Then if worst comes to worst, the 1/3s. Oh, 3/3 is 1. Forget that. And the 9. Oh, that's 3. Forget that.
I did a small brain. so I factored the 32.
With a GCF, and you pulled out an X.
Yeah.
Well, it would have been really nice though if it
Yeah.
had one.
All right.
I'm sorry. Well, at least last night it made you a little happier than the kids that had to tackle number 26 with a 9.
Yeah, I feel like 15, 20 minutes on this.
Ooh, but look at number 30. That had a GCF. Oh. But after the GCF, you still had a cube. But at least it wasn't a 4th degree. I mean, you only had to break it down once to make it a quadratic. And do you see how the negative one worked? I mean, the positive one didn't, but the negative one worked.
Yeah.
So you didn't have to go too far into the crazy possible ones.
Yeah.
And then you were able to do the synthetic, you get your quadratic, and then you factor.
Wait, Misty.
Yeah.
Why do you end up on number 26? Why do you end up putting 1 and 3 on the bottom?
Factors of the constant over factors of the leading.
Oh, okay.
Got it? That's their like little formula. That GCF did at least simplify that one a bit. Number 38. Number 38. They had you list out the possible rational zeros, factors of 4 over factors of 4, all the possible combinations. These are who would have been left if you had listed them all out. They had you go to your calculator next? No way. They had you go to your calculator next and then figure out where are the zeros, which you could have done with your calculator function. You would have found -2, -1/2, +1/2, and +2. And as you guys wrote those down, they were just asking, are they in the, yeah they are, right there and right there. All 4 of them are nice rational zeros. And if you had gone looking at all these places, you would have eventually found them all. Yeah.
So if you do it in the way that you showed before, the question that's right too, right?
Yeah. Because this way is just like what happens when you have the possible combinations. So they're just trying to figure out what actual numbers to test. So it's like the 1, 1/2. So that's okay. That's the way it makes sense to me. And 68 was did you guys notice he was a difference of squares?
I did, actually.
That would have made life a lot easier. And he was a difference of squares, and he was impossible. Oh wait, they wanted us to go to the imaginaries.
That was a fun one.
Oh, it kind of was, yeah. If you saw it. This one you can't factor and make it real, but you can factor and make it imaginary. And then number 96 was one of those weird using the rule trick things, right?
Okay, let's stop there.
Remember, you don't have to memorize those. You don't even have to know them super well. I just gave you a couple to let you see it. Did you guys notice I gave you a lot of odds? Like there weren't very many evens. And the evens were kind of the easier-ish ones. Because I wanted you to be able to look at calc chat in the back of the book. Does that make sense?
Yeah.
Okay. Monday, we didn't have time for questions today. I'll show you 96, sorry. He's upper, he's lower. But I'd love to hear him first thing Monday. Remind me, okay? So not the whole talking thing. I mean, I'll check in with you guys. Make sure that we're still I'll check in. So this weekend, try to narrow down your questions. And I think you could probably start with whole and vertical asymptotes to kind of help you out next week if you have time. If not, we'll catch you Monday night. Bye, guys. Good job, good job.
So I'm gonna come in after our walkthrough thing.
Okay. And that'll be pretty early, right?
It should be early.
3:30 or something.
Because I
Yeah, I saw you got stuck in there.
Yeah.